All right, now in this section of the lecture, we're going to talk about the dependence of rate on concentration and how we can represent that mathematically. So again, we know it's found that the rate of reaction depends on concentration of the reactants. It might depend on the catalyst and things like that. But again, what we want is a mathematical expression to help us explain the rate of a reaction so we can use it later on. So let's look at the reaction of nitrogen dioxide with fluorine to give nitrile fluoride. All right. So it turns out that if you run this experimentally, again, you can't tell what the rate is by just looking at a reaction, and we'll find out more about that at the end of this chapter. But it turns out that the rate of the reaction is proportional to the concentration of the NO2. It turns out that if you double the concentration of the NO2, the rate will also double. This sort of makes sense. You double the NO2, the rate doubles. Okay, if you also now, let's keep NO2 steady and we just change the F2 concentration. So it's also true that if you double the F2 concentration, the rate also of this reaction doubles. So doubling the NO2 will make the reaction double. Doubling the F2 will also make the rate double. And so, like I said a minute ago, we need a mathematical expression to show how we can write this relationship to concentrations. So it turns out that this is a rate law. The rate law is a mathematical equation that relates the rate of All right, so as a more general example, consider this reaction. The reactant A plus B and the catalyst C. And it could be any or all of these, but to write the rate law in the generic form, we're going to say, okay, the rate equals some constant times A raised to some power. And notice that little m is not the same as a, so it doesn't always mean it's the same as the coefficient. It could be, or it might not be, but it's important to realize that because that's probably one of the biggest mistakes students make. Times the concentration of B raised to some power. Again, n is not related to little b. They could be the same or they might not be. Times the concentration of the catalyst raised to some power. They're calling it P. Any of these powers could be 0, and you know that something raised to 0 equals 1, so that part would disappear. So it doesn't always mean that they're always related to every single thing, but they can be. So this is how we start. When we want to write a rate law, we say rate equals K times the concentration of A raised to some power times the concentration of B raised to some power, and if there's a catalyst, the concentration of C. And you'll get a better feel for it when we actually do this with some data in a few slides. Now, those exponents are frequently integers, and like I said, most likely in our case they should be integers. They could be 0, 1, 2, they could be 3, but they could also very easily be 1/2 or some fraction or some, but like I said, the ones we're going to be dealing with will be whole numbers so that we just get the gist of this and not get too complicated. But this is very important. They must be determined experimentally and are not gotten just by looking at the balanced equation. So again, the powers are not always, they can be, but are not always the same as the coefficient. And so that's a very important thing to keep in mind. All right, so let's just talk, first of all, what is the reaction order? The reaction order is just equal to the exponent of the concentration. So again, that's the power. So the little m or the little n or the little p, and it's determined experimentally, not from the balanced equation. So the overall order is just equal to the sum of all the orders. So let's look at an example here. So if we consider the reaction of NO, 2NO plus 2H2 to give us N2 plus 2H2O. Again, we don't know the powers because we can't look at the coefficients, but if experimentally we ran this reaction and the following rate was determined. So rate equals K to the NO to the second power times H to concentration. So if I want to know what is the reaction order, I would say it is second order with respect to NO. So if it's squared, we call that second order. It is first order with respect to H2. So it's first order in H2. It's second order in NO. And then if I wanted to know what is the overall rate, overall reaction order of this reaction, and it would be 3. So we would add the 2 plus the 1, so it's third overall. If you go back to slide 25, I think we had another rate law. Rate equals K times NO2 to the first power F2 to the first power. So that would be first order in NO2, first order in F2, and second order overall because you add them together. All right, so like I said, reaction orders are frequently whole number values, particularly 1, 2, also 0 sometimes. They can be fractional. They can even be negative and 0, like I said, but mostly we will be dealing with whole numbers. So just keep in mind, and I mentioned this just a minute ago, if something is 0 order, anything raised to the 0 power is 1. So basically a 0 order dependence means there's no effect on the rate. So increasing the concentration will not change the rate at all. That's a 0 order effect. Okay, so one thing that I'm going to ask you to do is to determine the rate law if you're given a bunch of data about a particular reaction. So as if we had run the reaction at different times and in different concentrations, found the initial rate of the reaction, and then we're going to determine the rate law from it. So it's called the method of initial rates. So what we're going to do, it actually involves running the experiment multiple times. You're going to take one of the reactants and vary the concentration and measure the initial rate of the reaction, and then vary the concentration of another reactant, keeping the first one steady. So you're only changing the concentration of one reactant at a time, measuring the rates, and then comparing what's happening for each different concentration. And so what we'll find is the order with respect to that reactant. So again, I'm going to do a number of examples, and you may want to rerun it. And I will say that your book kind of makes it even a little more complicated than it needs to be. And so hopefully as we go through, you can follow what I'm doing. All right, so keep in mind that if you double the concentration of a reactant and the rate doubles, we call that a first order. And looking back at the rate, remember that if rate equals something to the first power, then you can see that they vary in the same direction. So if you, let's say you increase the concentration, the rate should increase by the same amount because it's raised to the first power. So that would be called first order dependence, and it doesn't always have to be doubled, but if you double the concentration and the rate doubles, that would be first order. Or if you triple the concentration and the rate triples, that would also be first order. So that means raising it to the first power. Whatever you do to one thing, it mimics that on the rate. Now, what if you double the concentration and the rate increases by a rate of 4 or quadruples? Well, then that's second order. And if you kind of think about, again, if it's second order, that means you're squaring it. So if you take, say you doubled it to, you double the concentration, and then it's a second order reaction, so you're squaring that. So 2 squared is 4. So the rate is 4 times as fast because you're squaring that initial doubling of the concentration. And again, it doesn't have to be doubling. If you triple the concentration, 3 squared is 9. That would raise the rate of the reaction 9 times. And so, but just keep in mind, something raised to the second power, what does that do? You're squaring it. 2 squared is 4, 3 squared is 9, etc. If you double the concentration and you find that the rate increases 8 times as fast, then that is a third order dependence. And keep in mind that that would be, a cubic. So you double something, 2 cubed is 8. So if you double the concentration, but the rate increases by a factor of 8, then that is a cubic. That means you're raising the power to a 3. It's a cubic dependence. And of course, what I said just a minute ago, if doubling the concentration has no effect on the rate, then that's zero order dependence, because if you raise anything to 0 order, you get 1 back, so it doesn't have any effect at all. All right, so hopefully that makes sense. And so let's look at this data. So we've run various trials of this reaction, and we've measured the 2 reactants. And so if you sort of look at the different trials, trial 1 through 6, you can see that in trials 1, 2, and 3, the NO2 concentration stays constant, so we're not really evaluating it. But you can see from 1 to 2, we've doubled the concentration of NH4, and then from 2 to 3, we've also doubled it again. You don't always, this is actually a lot of data, so you don't really need this much, but you can follow what's happening. So I'm just kind of look at this data. Now, if you look at 4, 5, and 6, in that case, notice that the NH4 is staying constant and the NO2 is being changed. So from 4 to 5, we've doubled the NO2, and then from 5 to 6, we've again doubled it. So what we're going to do, though, is look at how the rate changes when that happens. So let me just give you a little bit of looking at this data, and then we'll probably follow it along in other as the other slides come up. But just think through what I'm saying here. Just look at trial 1 and 2. So trial 1 and 2, all we need to know is how is the concentration of NH4 affecting the rate of this reaction, because NO2 is staying constant. So we don't even have to worry about it for this moment. So if you look at trial 1 and then you look at trial 2, you say, okay, the NH4 positive has doubled. What's happened to the rate? Well, 5.4 times 10 to the minus 7th. In trial 2, it becomes 10.8 times 10 to the minus 7th. Clearly, that's doubled as well. So what are we looking at? We say, okay, if we double the NH4 concentration, the rate doubles. And we just got through saying that that would be a first order, meaning that the concentration's raised to the first power. That's a first order dependence. And then actually we don't need to look at it, but if we follow the same pattern and look at number 2 and 3, again, from 2 to 3, we've doubled the concentration, and from 2 to 3, the rate has doubled. So again, that just confirms what we just talked about. So it's first order with respect to NH4. Now, if we look at trial 4 and 5, okay, so we're not worrying about NH4 anymore because we're keeping that constant, but we're looking to see what happens when the NO2 is doubled. So again, to go from 4 to 5, we see that the concentration has doubled. What's happened to the rate? Well, the rate has also doubled. So again, that's a first order reaction. So let's kind of walk through the next few slides. We'll walk through what I just said again to kind of see how we write that down. So we always start out with the rate law, and the recommendation is always to write down rate equals K. Put the concentration of the first reactant in brackets raised to the little m power. You could use whatever. You could use X, Y, and Z. You could use whatever you want to use. But usually we use little m. No reason. And then times the concentration of the second reactant raised to the little n, because they can be different. If you have a third reactant, you would write that in brackets raised to, say, the little p. We use p instead of o because o looks like a 0, so it makes it more confusing. I don't know, you could use X, Y, and Z, the same thing. But the idea is to look at the rate with respect to NH4, what power, we're looking for the power. We're looking to find out what is little m. And then we're looking to find out what is the power for NO2, what is little n. So again, like I said, your book makes it a little bit more complicated, and if you just make sure that all the other reactants stay constant, you only have to focus on the one reactant that you're interested in for the moment. So let's look at this. So like I said, if you look back on the previous slide, the concentration of NO2, when the concentration of NH4 plus is doubled, as long as the NO2 stays constant, the rate also doubles. So we said that that is first order. So the rate is proportional to the concentration of NH4 to the first power. So that means little m is 1. So we can actually cross the little m out and put a 1 in there. And then, like we just went through a minute ago, when the concentration of NO2 negative is doubled, keeping the NH4 constant, the rate of the reaction also doubles. So that means little n equals 1. So it is also first power. So we would rewrite this equation as rate equals K NH4 positive to the first power, NO2 negative to the first power. So it's first order with respect to NH4, it's first order with respect to NO2, and it's second order overall. Now we can go back and actually plug numbers into this equation to find what the value for K is. So you can see here that if you plug in, take the first row, 5.4 times 10 to the minus 7th molar per second is the rate. K is what we're trying to find. The concentration for that trial is 0.01 for NH4 and 0.2 for NO2. So you plug those numbers in, you solve for K, and notice that the units, one of the molarities cancel, and so our units are inverse molarity, inverse seconds. And so the K equals 2.7 times 10 to the minus 4th. So if we plug that back in, the value for K, this is our final rate law. Rate equals 2.7 times 10 to the minus 4th per molar per second times the concentration of NH4 positive to the first power times the concentration of NO2 negative to the first power. And that's the rate law. So we already know how to put the concentrations in brackets, but what we're looking for are the exponents, and then finally to solve for the value of K. All right, so let's look at another example. H2O2 plus 3I negative plus 2H plus gives us I3 negative plus 2H2O. This time we have 3 reactants, so hopefully our data will give us all 3 reactants. So in fact, as we'll see on the next slide, a series of 4 experiments was run at different concentrations, and the initial rates of I3 were determined. And so we got the initial rate of reaction with varying the different concentrations. And so I think that's on the next data. So what we want to do is find out what is the reaction order with respect to H2O2, to I negative, and H plus, the 3 different reagents. So you're always talking about the reagents, and we don't worry about the reactants, the products, sorry, don't worry about the products. And then finally, once we have the rate law, let's calculate the K. So it's the same idea. So we always start out by writing the rate law, and the rate is always equal to K times the concentration of the first reactant raised to the M power, the concentration of the second reactant raised to the N power, and the concentration of the third reactant, if there is one, raised to the P power. What do we want to find? We need to find the values of M, N, and P, and then we also have to find the value of K. So this is our rate law. Now we have our data, and this time there's actually fewer data, but we can get what we need to by looking at it. So I'm just going to focus, again, like I said, your book sometimes tries to put too much in there, but as long as the other two compounds are staying constant, you don't even have to worry about them. So all I'm going to do is focus on experiment 1 and experiment 2, because H2O2 goes from 0.01 to 0.02. Notice that the I negative stays constant and the H plus stays constant. Do be careful to find them, because sometimes they're not always in the correct order, and you just want to make sure and find the right experiments. So notice that we have doubled the concentration of H2O2. What's happened to the rate? Well, it's doubled. And let me tell you that if you can't tell by looking at it, I think this is a pretty straightforward 0.01 to 0.02. Clearly that's doubled. 1.15 to 2.30. Clearly that's doubled. If you can't tell, what I recommend doing is always put the bigger one over the smaller one, make a ratio, and do that calculation and set it up. I think I have some of the coming up in just a second. All right, so experiment 1 and experiment 2, we see that H2O2 doubles and the rate doubles. What is that? First order. So that's a first order dependence. That means little m is 1. So we already know that, and this, just follow along for a second. So here's what I'm talking about. So as long as I and H are constant, we can say that that this is true. We could say that the rate of the second equation over the rate of the first is equal to the concentration of H2O2 from the second reaction over the first raised to the M power. So again, the rate equals the concentration M. Now if you plugged in those numbers for the second trial and the first trial, what you would end up with is this. So the rate, 2.3 times 10 to the minus 6 for the second trial over the rate for the first trial, 1.15 times 10 to the minus 6, gives you a ratio. You already can see that it's doubled, so it's going to give you the ratio of 2. But if you can't tell by just looking, this is what you do. Put the rate of the second over the rate of the first, and then in these brackets, because we're raising it to the M power, we put the concentration for the second trial over the concentration for the first trial, and then do the division. So we have 2 equals 2 to the M. What does M have to be to make this true? M has to be a 1. So that's what we mean by first order dependence. Now, I think your book likes to put in all the other ones, the I negative and the H plus, and show that they cancel out. But because they're staying the same, we don't even have to worry about them. So don't make it too complicated for yourself. So again, if you can see that it's doubled, and that the rate's doubled, you know that's first power. You just put a 1 for M. But if you can't see it, this is the way you set it up. You put the two rates. I always put the bigger one over the smaller one, because it will make it won't give you fractions, which can be really complicated. So always, it doesn't matter what order you put them in, always put the bigger one over the smaller one, and then the bigger concentration over the smaller concentration, raised to the M power, and solve for M. So M equals 1 in this case. So I would just go back to my rate law, and I would cross off M, and I would put 1. All right, now let's look at just focusing on the I negative. And again, you have to be careful, because you want to make sure that the other two are staying constant. So in fact, if we look at experiment 1 and experiment 3, you can see that H2O2 stays constant, H plus stays constant, and we're doubling the I negative. What's happened to the rate? If we look between 1 and 3, again, you can see that it's doubled. So this is also first order. But let's go through the calculations. All right, so here are the calculations. So again, if we look at the rate from trial 3 divided by the rate for trial 1, Always the bigger over the smaller. The concentration for trial 3 over the concentration for trial 1 raised to the n power, because this is that second segment of our rate law. Again, if you solve, do the ratios, you have 2 equals 2 raised to the n, and so n has to be 1, so it's first order again. So we can cross off the little n and put in a 1. Now let's look finally at the H plus concentration. So again, focus really carefully and see which 2 experiments you want to use. Well, number 1 and number 4. So notice that the H2O2 and the I negative have stayed the same. The H plus has doubled. What's happened to the rate? Well, you can see from 1 to 4, it's stayed the same. Well, let's go through the math and see what happens. So if you can't, do you remember what that is? It's 0 order, but let's go through the math and see how you can figure that out. So again, since the rate is unchanged, it's 0 order, but if we put it into the math, we can see that better. So again, the rate of the 4th trial over the rate of the 1st trial, the ratio is 1. So it hasn't changed. The concentration from trial 4 over the concentration for trial 1 is 2 because we've doubled the concentration. So what does P have to be to make this equation true? P has to be 0. So again, it's 0 order. So now that we've looked at the rate law, we say, okay, rate equals K times H2O2 to the first power times I negative to the first power times H plus to the 0 power. Since H plus to the 0 power is equal to 1, we can actually cross it off. And so the actual rate law is the second line. K H2O2 to the first power, I negative to the first power. And then by taking, actually you can take any of the experiments that you want to, but just go ahead and pick number 1 to be easy. Plug those numbers in. So if we calculate the rate constant by substituting the values in, you can see that we have the rate, 1.15 times 10 to the minus 6, equals K times 0.01 to the first power, times 0.01 to the first power, times 0.0005 raised to the 0 power, so we can ignore that. So if we take 1.15 times 10 to the minus 6 divided by 0.01 divided by 0.01, we're going to find the value for K. So there you go. Notice that the units that will end up canceling will end up with inverse molarity, inverse seconds. So now 1.15 times 10 to the minus 2, or 0.0115, is our K value. So this is what we're looking for when I say determine the rate law using the law of initial concentrations. The units of K can be very messy. So they depend on what type of reaction it is. Now, rate should always end up being molarity per second. That's just a unit for rate. So the K value has to be such that it cancels out any other concentrations. So notice, and if you really have a hard time with this, just kind of come back and look at this slide that has it already figured out for you. So if you've got a first order reaction, rate equals K times A. Since rate is has to always be molarity per second, then K, since A is already molarity, K is just going to end up being inverse seconds. So molarity over seconds equals K times molarity. The molarities will cancel, so K has to be inverse seconds. If the reaction is second order, then here's the equation. We want the rate to be molar per second. So K has to be whatever units that when multiplied by molarity times molarity, because B is in molarity, C is in molarity, K has to be, and this just rearranges it, K, one of the molarities cancel out, and so our K value will be inverse molarity, inverse seconds, because we have to cancel out one of the molarities. If it's third order, and actually the last two examples were second order because our K's ended up being inverse molarity, inverse seconds. Our third order, notice that again, because we want molarity per second to be the rate, the K has to be units that cancels out two of the molarities. So K has to be molarity inverse molarity squared inverse seconds. So if you're having trouble, just go and see what kind of order you have, and your K, the units for your K will be here on this slide. So I have one more example here, so let's just work through it. All right, find the rate law for the following equation given the data in the table. All right, so the first thing we want to do is write our rate law, and so we say K equals ClO2 raised to the m power. We don't know what the order is, times OH raised to the n power. Those are our two reagents, and if you're not sure which ones they are, you just see which ones are given in the data. Okay. So basically we're trying to find M and N. So we're going to focus first on the ClO2. Now notice that these are in a little bit different order, so don't let that throw you. Let's compare experiments 1 and 2. What happened? Okay, the OH is constant, so we're not going to worry. So ClO2. This time reaction 2 is 0.02 and reaction 1 is 0.06. So to go from 2 to 1, we've tripled the concentration. And what's happened to the rate? Well, you may not be able to tell. So we can always set it up, like I said before. So you can say, all right, well, in this case, I'm going to put the rate of 1 over the rate of 2. Why is that? Because it's just easier to work with numbers that aren't fractions, so I'm always just putting the bigger one over the smaller one. So the 0.06 divided by the 0.02, well, that's the concentration, so that goes on the right-hand side. And you want the rate of number 1 divided by the rate of number 2. So let's plug that in. Okay, so the rate of number 1 is 0.0248 divided by the rate of number 2, 0.00276. The concentration of Cl2 for trial 1 is 0.060 divided by the concentration of trial 2, 0.020. So now if we do those divisions, we end up with 9 equals 3 raised to the m. So what does m have to be? Okay, there we go. M has to equal 2. So little m equals 2. So that's second order with respect to ClO2. So I hope you follow what I did. You always put the concentration in the brackets raised to the power and then the rates on the left. Now you might have already been able to see that to go from 0.00276 to 0.02448 is 9 times. You might not have been able to see it, but you just divide it out if you can't see it. You find out what is the ratio, and it's 9. And so we've tripled the concentration. What's happened to the rate? It's gone up by a factor of 9, and so that is second order. 3 raised to the second power is 9. So we go ahead and cross off the M. It's second order with respect to ClO2. Now, let's focus on the OH negative. So already you see that I've written my rate law in, and I've already changed the M to 2 because we know that that's number 2. So now we're trying to find what is little n. So now what we need to, again, be careful to see which two rates. And you might pick number 1 and 3 and say, okay, look, OH negative triples. Well, be really careful again. You want to make sure that you pick the ones where the ClO2 stays the same. So that would be actually reaction trial 2 and trial 3. Trial 2 and 3, ClO2 stays the same and OH negative triples. So again, and what happens to the rate? Well, again, you might not be able to see that. You might, depends on your math intuition. Actually, to go from 0.00276 to go to 0.00828 is a triple. You might not be able to see that though, so let's set it up again. So the rate of number 3, and again, I'm picking 3 to be on top over number 2 because 3 is bigger than 2 in this case. If they were the other way, I would do 2 over 3, whatever gives you the whole number. So rate 3 over rate 2 equals the concentration of OH for 3 over the concentration of OH for 2 raised to the n power. We're trying to find n. So if you plug those numbers in, 0.00828 divided by 0.00276, that again is going to give us the number 3. And then 0.090 divided by 0.030 is 3. So what does n have to be to make this equation true? N has to be 1. So when the concentration is tripled, the rate is tripled. That's a first order. N equals 1. And again, it's first order with respect to OH negative. So now I'm just going to change N to 1. And there's my rate law. Now, finally, to get My K value, I just go through and I plug in one set of data. So I'll plug in the first set, 0.0248 equals K times, and don't forget, because it's squared, don't forget to square it, 0.060 squared times 0.030. So if I take 0.0248 divided by 0.060 squared divided by 0.03, I'll find K. And it's basically 230. What are my units? Again, we want the rate to be molar per second, so you have to have the inverse second as part of your units of K, and then you want as many molar as one less than the number of molarity that you have. So in this case, 2 plus 1 is 3, so m to the negative 2. So that will cancel out 2 of the 3 molarities, and so K, so rate will be molarity per second. So what is my final answer? Rate equals 229.6, molarity to the negative 2, seconds to the negative 1, times ClO2 squared times OH negative. The thing now is we have our rate law. So what if we want to know what will happen with even different concentrations than what we're given? We can plug them in. All right, so what will the initial rate of reaction be if ClO2 concentration is 0.01 and OH negative is 0.015? So we just want to know what will happen if that's the case. Well, now you can just plug that in. So rate just equals K, 229.6, times ClO2, 0.01, squared times 0.015. Do that calculation and you get the initial rate will be 3.4 times 10 to the minus 4 molar per second. And the units of rate is always molar per second. Notice that K will cancel out 2 of the molars, and then we have 1 more left, so that's where, and then the second is in the denominator already.